Hello, my name is Neil Compresso, and today we will talk about synthetic latex. Let's talk about its manufacturing process. Before any reaction begins, the primary ingredients, monomers, solvents, and chemical agents are measured and prepared. Monomer feedstock. The core ingredients are selected based on their desired latex properties. The standard latex. This involves styrene, a liquid, and butadiene, a gas liquefied under pressure. Emulsification water. High purity demineralized water acts as the continuous medium that suspends the particles and dissipates the heat generated by reaction. Surfactants. Emulsifiers. Soap or fatty acids are added to lower surface tension, allowing the oil-soluble monomers to disperse uniformly into tiny droplets within the water. Emulsion and reaction. This is where the actual synthesis occurs inside a heavy-duty agitated reactor vessel, charging the reactor. The water emulsifiers monomers and molecular weight regulators modifiers are pumped into the reactor and vigorously agitated to form a stable emulsion. Catalyst initiator injection. A water-soluble free radical initiator such as potassium persulfate or hydrogen peroxide is injected to jumpstart the polymerization reaction. The initiator breaks down into free radicals, which migrate into the soap micelles swollen with monomers. The monomers chemically bond together, forming long-chain polymers. This reaction is highly exothermic, generates heat, so cooling jackets around the reactor strictly regulate the temperature, typically kept cold around 5 degrees Celsius for high quality rubber or hot around 50 degrees Celsius depending on the grade. Step 3. Short stopping and separation. Stripping. The reaction must be halted before all monomers are consumed to prevent the polymer chains from becoming overly cross-linked and brittle. Short stopping. When the monomer to polymer conversion reaches a specific target, usually 60% to 80%, a short stop chemical like hydrochrominoin is injected to kill the free radicals and terminate polymerization. Degassing. Butadiene removal. The unreacted, highly volatile butadiene gas is flashed off under reduced pressure and captured for recycling. Steam stripping, styrene removal. The mixture is sent to a stripping column where steam is injected. The steam vaporizes the remaining unreacted styrene monomer, separating it from the latex so it can be condensed and reused. Step 4. Conditioning and compounding. The fabricating stage. The raw polymer base is modified to meet specific commercial shelf life and performance standards. Stabilization. Antioxidants and stabilizers are blended into the liquid latex to prevent atmospheric oxygen, UV light, and heat from degrading the polymer chains over time. The illustration shows the primary stabilization mechanism utilized during emulsion polymerization to maintain stable synthetic latex particles as displayed. pH adjustment. Ammonia or other alkaline chemicals are added to adjust the pH, ensuring the liquid emulsion remains stable and does not prematurely coagulate during transit or storage. The picture details mechanisms of pH switchable stabilization and coagulation, specifically for synthetic carboxylated latex systems. Concentration. If a higher solids content is required, the latex is concentrated using methods like evaporation or centrifugation to remove excess water. Finally, finishing and quality control. The final steps to ensure the synthetic latex is uniform and ready for industrial application. Blending and filtration. Multiple batches are often blended in large storage tanks to ensure product uniformity. The liquid is then passed through fine mesh filters to remove any macrocoagularium or grit. This picture shows mechanical setup of a classic industrial agitation system coupled with automated microfiltration used for synthetic latex compounding, packaging, or coagulation. For liquid latex application, by chance adhesives, carpet backing, dip gloves, the liquid emulsion is pumped directly into tanks, drums, or totes. For solid synthetic rubber, the latex is deliberately coagulated using acids or salts, washed to remove residual chemicals, dried and hot hair, and pressed into ballast of solid rubber. Let's talk about the products. Textiles and floor coverings, carpet backing. This is actually the single largest market for styrene butadiene latex. It is used as a heavy structural adhesive that locks the carpet tufts into backing fabrics, keeping the carpet flat and durable. Artificial turf. Much like carpet, the synthetic grass blades are secured to the base layers using a thick coating of weather-resistant synthetic latex. Dip goods and medical supplies. Natural gloves. Medical and industrial latex-free gloves are made from acrylamide butadiene latex, natural rubber. They offer excellent puncture resistance and protection against oils and acids. It also works for coated work gloves. Knit safely gloves are frequently dipped in synthetic latex to provide a grippy, durable, and puncture-resistant coating on the palms and fingertips. Construction and adhesive. Waterproof coating and sealants. Synthetic latex is a primary ingredient in concrete sealers, roof coating, and waterproof membranes because it locks water while remaining flexible enough not to crack when buildings shift. Mortar and cement additives. Adding liquid latex to cement mixes increases their adhesive strength, flexural strength, and water resistance, often called latex modified concrete. Consumer goods and comfort. Synthetic foam mattresses and pillows. Many latex foam mattresses use a blend of natural and synthetic SBR latex. It is whipped into a foam and baked, providing a highly responsive, breathable, and supportive sleep surface. Shoe soles. Many casual shoes and sneakers use dense molded synthetic rubber derived from coagulated latex to provide flexible, long-lasting grip. Paper and packaging. Glossy paper coating. The smooth, shiny finish on high-quality magazine papers, brochures, and cardboard packaging is achieved by coating the paper with a mixture of pigment and a synthetic latex binder, usually known as styrene acrylic. This keeps the ink from bleeding and makes colors pop. In conclusion, before production starts, base chemical ingredients called monomers, like styrene and butadiene, are chosen for the recipe. These oils-based chemicals are mixed into pure water, which acts as a liquid base and keeps the mixture cool. Finally, the chemical soap surfactants are added to lower surface tension, allowing the oil-based ingredients and water to blend smoothly into an even mix of tiny droplets. Inside a heavy-duty reactive vessel, the water monomers, emulsifiers, and modifiers are vigorously mixed to form a stable emulsion. A water-soluble initiator, like hydrogen peroxide, is then injected to jumpstart the polymerization process, causing the monomers to chemically bond into log-change polymers. Because the chemical reaction generates intense heat, cooling jacket wraps around the reactor to strictly regulate the temperature, keeping it cold at around 5 degrees Celsius or hot at 50 degrees Celsius depending on the grade of the rubber being made. To prevent the polymer change from becoming brittle, the reaction is intentionally halted before all the ingredients are used up. Once the mixture hits a target conversion rate of 60 to 80%, a short-stop chemical is injected to kill the reaction. The remaining unreacted material are then separated and recycled. Volatile butadiene gas is removed to depressurize degassing, while unreacted styrene is vaporized and stripped out of oozing steam, leaving behind clean latex. The raw polymer base is modified to meet commercial standards and extend its shelf life. Antioxidants and stabilizers are blended into liquid latex to protect the polymer chains from degrading due to oxygen. UV light or heat, ammonia, or alkaline chemicals are then added to adjust the pH, keeping the liquid emulsion stable during storage. Finally, the application requires thicker products. Excess water is removed using evaporation or centrifugation to concentrate the latex. To ensure product uniformity, multiple branches of synthetic latex are blended together in large storage tanks and passes through fine fresh filters to remove any microcoagulation or grit. Depending on its intended end use, the finished product is then processed in one or two ways. It's either packaged directly into tanker drums or totes for liquid applications, or it's deliberately coagulated into acid or salts, washed, dried, and pressed into bales of solid synthetic rubber applications. And finally, its properties can be customized for optimal water resistance, durability, and adhesion. Its function as the critical backing binder for commercial carpets and artificial turfs, as well as puncture-resistant protective layer of medical gloves and coated work gear. Furthermore, its flexibility makes it a key additive for waterproofing structural sealants, sticky tape adhesives, and reinforced concrete mortar, while its mechanical resilience provides the supported cushioning found in synthetic foam mattresses and molded shoe soles. Paper and packaging industry heavily relies on synthetic latex as its pigment binder to create a smooth, high-gloss finish required to prevent ink bleeding on premium magazine pages and cardboard packaging. This concludes my presentation. Thanks for watching.